Okay, so I guess we'll get started. So last week I just left you guys with this problem right here, right, that was sort of representative, I think, of some of the more challenging components that are going to come up in Organic 2, um, and sort of illustrate, I think, the level that eventually you guys are going to sort of be thinking at. And what I told you guys last week, right, was that thinking about how this process might go on, based upon the knowledge that you guys currently know. Without dealing with stereochemistry, that might be more in line with what I would expect out of somebody this semester, that would be in the B range. Ultimately, if you want to be in the A range, there's going to be an additional component this semester that's going to deal with a little bit more complex stereochemical processes, which will require a bit of heightened artistic capabilities. That's going to draw as well on some of the conformational information that we learned in Organic Chemistry 1. And so let's sort of discuss this problem at the onset. Right? I threw this up here in part because it draws in some of the things that you guys have seen in the past. And last semester, when we talked about functional group modification, the real only functional groups that we focused on primarily, right, were alkenes and alkynes, right? And when we look at these molecules, we see, indeed, a couple alkenes. We also see this reagent that I'm showing you here. What is that molecule? Does anybody know? It's formic acid, right? It is a carboxylic acid. So generally, we don't necessarily think of carboxylic acids as being strong enough maybe to protonate alkenes, but in this mechanism you need something to drive it, and probably over time or with a little bit of heat, or potentially even if it's catalyzed with something, this is ultimately what's going to happen. And so when we look at this reaction, we're trying to think about what's going to happen here. We've got a molecule with a variety of different functional groups on it. Specifically, I'm pointing your attention to the two alkenes, and you have an acid. Right? And so the first question that you guys sort of may want to ask yourself, giving yourself a little bit of flexibility, because again, we have to remember that reactions are dynamic. They can go in both ways, oftentimes going to a thermodynamic product, but at least the first guess estimate to potentially lead us down the right path. We may want to ask the question, of these two alkenes, which one might actually be more likely to react? And in this chemistry, the alkene is going to behave as a base, right? So which alkene of these two might you guys think would be more prone to getting protonated? Thoughts? Abraham, you look like you want to take a guess.
This might be wrong, but I would say the first one, because the alkene would be on tertiary center.
Right, and so say that one more time.
The alkene would be on a tertiary center, and that would be a very stable carbocation if you were to react.
I think you're seeing it. This is oftentimes where talking chemistry and drawing chemistry can be a little bit more complicated. So if you were to protonate this alkene, right? I think you're thinking of the next step. If you were to protonate this alkene, you have an option of putting the proton here or the proton here. Wherever I put the proton, the other carbon is going to be where the carbocation is. And I think this is where you're going. Is that ultimately that sort of tertiary carbocation is something that you can actually put here. Whereas on this carbon, both of them would not be, right? Would not be tertiary carbocation. So you have this initial sort of inkling that, hey, I can protonate one of these and leave behind a tertiary carbocation. This is something when we talked about Organic Chemistry 1 and some of the reactivity, regioselectivities that we dealt with in Organic 1, this was one of the big things, right? Alkenes, sort of Zaitsev's, right? Or, excuse me, not Zaitsev's, but sort of Markovnikov, right, addition is based upon the idea that when you protonate an alkene, or when you react something electrophilically with an alkene, the carbocation character is ultimately going to be at the more substituted carbon. There's another aspect, though, about this. Yeah? So yeah, let me draw this out. Sometimes drawing out can be helpful. Right, so this carboxylic acid is in conjugation, right? And so one may want to argue, and it's not the right argument, but it's a rational argument, especially at this point in organic chemistry, that this carbonyl, if you were to say, for example, protonate this, and put a carbocation here, right? So I'm just going to do both things right now. So if we protonate here, one option that we like, right, because it's tertiary. Another option that's being brought up is potentially the other alkene due to potential resonance. And so one might argue that if I were to put the proton, say for example here, and put a carbocation there, I might have resonance. And that's true, right? And that's certainly true that we would have resonance forms. But this goes back to one of the discussions that we discussed earlier. Right, that if I were to move those electrons there, right, you got to be careful. A common mistake that students will make is they'll screw up their charges. But what are we doing here by doing this resonance form? We're putting a positive charge on that oxygen. Not only are we putting a positive charge on the oxygen, what else are we doing? What else is maybe problematic with that oxygen? Rachel? Yeah, I guess none of these cases have octet rules, but yeah, I guess that I was thinking, but that's maybe not completely fair comment to make at this point, because everything, once we protonate it, we kind of don't have in any of these cases a full octet. But yeah.
Also with an enol form?
So this is not, so we're not getting into the enol keto tautomerization here because it's cationic, so it doesn't quite fill into that. But this resonance form, I think that the bottom line is this is not a resonance form that's going to be that good. And so while it exists and it's worthwhile to sort of see that it exists, it's really not a good resonance form. And it ends up being trumped, furthermore, by something else that carbonyl that actually has the opposite effect. Yeah.
Is it any resonance better than no resonance?
That's a sort of a question that's difficult to answer because some resonance is better than no resonance, but it's a more complex question that we're asking here, right? Because there's lots of different scenarios going on, right? So no. I'm going to stick by that answer, no. Because in this case, there's something else that trumps it. Some resonance is better than no resonance, but if something else is going on that makes it worse the other way, which is what's happening here, that's not going to be the case. And I'll maybe explain it in a moment, yeah.
But that has to do with stabilization, right?
Right.
It's just too unstable.
Right, so it's not a major contributor to the resonance. So, but the question was brought up, is no resonance better? And so maybe in specific questions that we're asked. But there's a bigger problem here that will often come up, right? And it reflects, yeah, Henry.
Does that have anything to do with the octet effect?
Yeah, yes, to a certain extent, maybe even more so. If you think about, and what are you getting at, Henry? The carbonyl, right?
Yeah.
Right? That this carbonyl, if we start to think about the dipole of that carbonyl, where is the dipole of that carbonyl? It's going towards the oxygen, right? And so if that dipole is going towards the oxygen, you're generating a delta pos here and a delta negative there, right? And so one of the things that you generally want to try to avoid, right, is to avoid putting one positive charge next to something that's already maybe electron deficient, right? In this case, sort of two positive charges next to another wouldn't be that good, right? That's not necessarily something that we would want to do. So in this case, the inductive withdrawing effect will outweigh, in fact, the will outweigh this sort of resonance form that we have. All in all, I think the point remains that the carbocation that's tertiary is going to be the one that's beneficial, right? So here we are. Okay, of the two options, we'll maybe come back to these sort of alpha beta unsaturated carbonyls at a later point. I just want to sort of try to get through this mechanism. Okay, so we've got our carbocation, right? And even before we started to decide that, right, for any of these questions that we go on, mechanistic questions or otherwise, we're oftentimes looking at it as many hints as we can possibly get, right? So even if you didn't know where you'd want to protonate at first, there could be other hints as well that might tell you where things may want to go. And one of the common ways to go about thinking about mechanisms, right, would be to try to track where everything is, right? Is this a simple ring closing reaction? And if so, where's the new bond, right, that's being formed, right? Where are the carbons? Where are the carbons here? Where might we expect those carbons to be there? And if we number them and look through them, that might provide us with a hint in terms of which bond is going to form, right? And if we know where that bond is going to form, then we can begin to think about perhaps how certain intermediates might help us form that bond, like carbocation, which would be a pretty good intermediate, right, to form new bonds, right? And so, I always think it's a good idea to sort of number our carbons, right? And so we're making a 6-membered ring here, right? And we have 1, 2, 3, 4, 5, 6. And we've got a 6-membered ring, right? In addition, if we look at where carbon 1 is bonded to 2 methyl groups. So there's a good chance that this is carbon 1. What do you think this carbon is? I heard 6. Why do you think it's 6? 6 carbon has a carboxylic acid appended to it, right? Carbon 2 doesn't have anything appended to it. So there's a good chance, right, that this carbon here will be carbon 6, carbon 5, carbon 4, carbon 3, carbon 2. And so really at the end of the day, the bond that we're looking to make, right, is going to be the bond between carbon 1 and carbon 6. Okay? Make sense? Right? So if we're looking at this intermediate that we have right here, right, we have a carbocation, right? We can sort of number this again if we want to. 1, 2, 3, 4, 5, 6. And the bond that ultimately we want to form is between here and here. Now, again, I'm just going through strategies of problem solving that might work out here. Everybody's brain works differently, so maybe this will be helpful for some people. Maybe you don't necessarily need to do this, but one of the important things about organic chemistry, and one of the reasons why we spend a large portion of Organic Chemistry 1 working on redrawing molecules and making sure we don't screw up redrawing molecules in different fashions, is that oftentimes within organic chemistry, redrawing the molecule in a slightly different way can oftentimes help us see, right, what's going on. So we look at this structure, and we see that it's a 6-membered ring, right? What we can maybe do here, right, is sort of redraw this molecule. Positive charge there, that's 1, 2, 3, 4, 5, 6. You see? Right? And by drawing it in this fashion, it makes it a little bit perhaps easier to see the next reaction that we need to do. What's the next reaction we want to do? Skander, what do you think? I'm not going to ask you, we went over it in subgroup. Somebody else. Somebody that hasn't talked yet.
That alkene on level 6, is that
Yeah, the alkene on 5, 6, that's where our electrons are, right? We need electrons to make a bond. The only real electrons that we can maybe imagine or rationalize here are those double bond alkenes, right? And so, again, maybe I can make it even easier to see if we take those bonds, make them red, right? We're going to make that bond. Okay, so what I want everybody to try to do is draw the product that would emanate from this structure. So this is that, right? If we do this, right, what we've done is we've taken those electrons, the set of electrons in the double bond, right, with the pi bonds. We're going to make a bond to 1. This is 1. 1 still has the gem dimethyls. This one has HO2C, right? And when we make that bond, what happens?
you get a plus charge on
Carbon which one?
the 5.
Carbon 5.
Then you take that formic acid, which already lost off, how you use the
Right. Exactly. So let me just do this, just to So save on board space to make it cleaner.
Formic acid, that's the ant poison. I mean, the stuff that ants create, right?
It's formic acid is everywhere. Yeah, it's pretty common, probably. Right, and so exactly. So once the formate, right, reacts with the cation, right, that's going to lead us here. Okay, so this is something that, you know, it's not necessarily the easiest mechanism in the world. It's not like adding HBr, right, across the double bond. Adding HBr across the double bond is perhaps a mechanism that I could teach Lucy to draw, right? And so you can memorize it, right? But you guys having a more fundamental understanding, more complex mechanisms such as something like this, are something that I would expect of a student that's about a B student in this class, right? If you're going to get a B in this class, these sort of a little bit more complex mechanisms should be something that you are comfortable doing and that you can do well, right? A's in this class, right, are going to have to take this a step further, right? And again, these are just representative. I'm not saying that if you can't do this, but just in general, I'm just giving you sort of a viewpoint of what my expectations are. The A student's going to be able to tell me about that stereochemistry, okay? And now, the caveat to this is I sent you home and I had you think about it. I didn't necessarily expect anybody, unless you did a little bit of research, to know exactly how this came apart. But the idea is that I'm going to show you, right, why this stereochemistry is the way that it is. And the idea would be that you should be able to explain that, perhaps in more complex scenarios, once I sort of show you. And the other point of this is it's going to involve chair conformations, right? And chair conformations is going to resort back to how configurational stability within chairs can actually influence transition states. And the lower transition state is the one that's going to form, and if a more stable transition state ends up being the kinetic product in many instances, right? Okay, so the hint perhaps here, right, is maybe this intermediate that we have right there, right? And it's the idea that we have a 6-membered ring that we're forming, right? And the question sort of becomes, how is the stereochemistry what it is and why is it? And so we'll see in certain cases where we can draw molecules and we can draw reactions flat, specifically once we get to pericyclic reactions. This is one of the things that a little bit more challenging. Students tend to spend quite a bit of time on because it does take time to get a handle on. But in general, you know, when you see these 6-membered, in this case, cyclization, right, then it may be possible that that transition state can be invoked by chairs, right? And so if we think about what this chair would look like, oops, right, we're going to have right, we're going to have a carbocation that's going to look something like this. Notice how, let me just make it a little bit more apparent. Sometimes I often like to draw dots, right? And what's key about this intermediate, so I'll often just draw a dotted line to sort of complete my chairs when I'm looking at this to sort of show that's where the bond is ultimately going to form, right? And when this happens, right, the electrons that we had in here are ultimately going to become the electrons that we have here. And I want to point out something specific about this transition state, which we're going to come back to later on. If this were a chair, if I were to draw this molecule, if I were to draw this, an actual chair conformation here, it's not a very good chair. I'm usually better at drawing chairs than I am right now, right? But sort of this carbon here, right, you can draw on your proton as well, right? If I were to effectively substitute this for this, just to sort of give you guys a more graphical representation there, the orientation of that trans double bond, even though it's not an actual chair, would you say that carboxylic acid there is more equatorial or more axial? Yeah, it's more equatorial. And so we'll see this quite a bit, that in pericyclic reactions in particular, whether we have a trans or cis double bond, right, that's going to ultimately end up being forced into a position where on the final chair conformation, right, it's going to be either axial or equatorial. That make sense? Right? Now, in that process, we're going to be generating carbocation that you see here. And I'm going to try to break this down. It's actually more of a concerted process, so maybe I'll go back and redraw it in the concerted process afterwards, but let's just break it down into individual parts. When that cyclizes, right, we're going to end up with this carbocation. Assuming that carbocation can't relax, the formate has to come in, as we just said. Do you think that the formate is going to come axial, or do you think the formate's going to come equatorial? Which approach might be more accessible? Why do you think so? I'm hearing both. And this is maybe a little bit tough to wrap your head around. So let me draw those approaches. Okay, the axial would be here, coming from the top. The equatorial would be coming from the outside. Right? So the equatorial would be coming more in that direction. Rachel.
I forgot the term, but it's a little out of the way from nothing. If it goes in axial, if it goes in equatorial, there's nothing.
Yeah, so maybe you're talking about, I don't know that you've heard of, syntentane interactions. I mean, that's kind of maybe you're talking about 1,3 diaxial. That's the term, I guess, that would have come up more likely. So yeah, sort of a 1,3 diaxial interaction. I mean, in general, it's the 1,3 diaxial interaction that helps explain why molecules don't like to be axial and why they prefer to have groups in the equatorial position and lower in energy, right? By that same theory, right, it should make sense that a group that's approaching a cyclohexane, right, which would make sense for that same reason, that a group approaching a cyclohexane, having multiple options on which to approach it, right, would probably prefer to be in a pseudo-equatorial position. And so the formate's going to be here. The ester's going to be here. Your groups are going to be there. When we open that up to the 6-membered ring, right? If we're looking down from the top, think about our protons, right? Looking from the top. Here, we're going to see the proton first. Here, we're going to see the proton last. So the stereochemistry of those two groups are, in fact, trans. If I changed the stereochemistry here to be cis, right? If I changed that stereochemistry and made it cis, now this group would be pseudoaxial, right? Again, at the transition state. I'm given the timing of things that we have to go through. I'm not going to draw the entire one, but maybe at a later time, because I think it's fine to explain it to you guys the way that I did. Hopefully that will make sense. But if this was now cis, at that intermediate, the group would be down, right? So this would be down, and then those two would be on the same face as one another. So the point that I'm bringing up here is that the stereochemistry of the alkene ends up transitioning, right, to stereochemistry in the product. Not learning this right now, but we're going to learn it pericyclic chemistry, and this is something that's going to be a major component later on in the semester as just a representative example. Okay? You had your hand up. Yeah.
Wouldn't the equatorial position be blocked by the formic acid?
The formic acid is what's adding.
That-
Oh, the carboxylic acid
If
here?
you would like draw it out, then it's bigger.
Well,
Wouldn't it
so if I had a model here, right, it's all around the outside. So the interaction that you may get here, right, if we do our chairs, right, the interaction that you're kind of referring to, you do have a pseudo-Gauss interaction.
And then also the
But wait, hold on. If you came from the top, you'd have that same pseudo-Gauss interaction with this, but you'd also have the same pseudo-Gauss interaction here. So just go back and revisit chairs, right? The Gauss, they're always, if you have two groups on a chair that are both equatorial, they're going to have Gauss. But it doesn't mean that they want to escape one another to both be axial, because then they have additional Gauss interactions. Make sense?
So
Okay,
the
except in rare cases, like the classic example is 2T-butyl groups would not want to be gauche, so that's a rare example where that chair wouldn't be.
would always want to be equatorial.
What's that?
Like the group attaching will always prefer to attach.
Yeah,
equatorial.
so I'm never going to say always. So what we do in organic chemistry and what we do in chemistry is we're trying to develop oftentimes models, specifically in synthetic organic chemistry, to explain outcomes, reactivity outcomes. You know, the truth of the matter is that anything that we come up with is simply a model that works best, that helps us predict, and that's been tried and true over time. And so there's always exceptions to the rules. But this is just a classic example of a polyene cyclization model that invoked a chair conformation and involved alkenes. And I thought it would be a good example to show because you guys have learned about chairs, you guys have learned about alkenes, and this puts it into a little bit more complex setting to sort of illustrate what's going to be coming down the pipeline in terms of the relative complexity. Yeah.
Can you repeat what you said about the transition state and how they would have affected something that would be cis or versus trans?
So it's a little bit more complex. So what's happening, and I'm not going to draw it, but what's happening is both these steps are happening at the same time. It's actually or at least the model that's been invoked is that it's a concerted process where the formate is adding. It's all concerted, where the formate is adding while this bond is forming. And so I'm not going to bother showing that. I'll just tell you guys that it's sort of a composite of these two steps all tied together, right? Because the outside face, it wants to be, so equatorial, as you guys know, an equatorial group is more stable. It's away from sterics. By that same theory, and by that same, if you can understand that, then you should understand that the approach of a group, if a nucleophile is attacking a cyclohexane, and it's coming, quote-unquote, pseudo-equatorial, right? That's also generally, not always, but generally going to be lower in energy than if it's trying to come from a more pseudo-axial environment. So that's about the approach of the formate. This here, it's Brianna, right? Brianna. This group here, right, is basically set because you want to have a chair transition state. And if you think about it, right, there's a sort of a parallel here, right? What's more stable? A trans double bond generally or a cis double bond? Trans double bond. What's more stable generally? An equatorial substituent or an axial substituent? Equatorial. And so there is this sort of parallel here, which I don't think is completely coincidental, right? Where the positioning of this group being trans in the chair conformation basically means that if you envision it like here, the transposition is pseudo-equatorial. So when you're done with the product at the end, it's equatorial. When it's cis, if it was down where that proton would be, that would be pseudo-axial, right? So it would end up down here in the axial position. And this will come up again later on with pericyclic reactions. So we'll revisit this concept in about a month and 5-6 weeks, okay? But it's just, I think it's a good primer to sort of have you guys know what's coming, okay? All right, so let's get our juices flowing, right? All right, let's so we're going to start today. Well, we started with this. We're going to continue today. That's not working.
It's not.
Can I ask somebody to just give me a heads up when there's like? Oh, I have it here. It's 10 o'clock. That's right. Okay, I have 10:02. So that means by my clock I get to go over by 2 minutes. All right. Okay, so as last semester was kind of lined up by functional groups, we're going to spend the first few lectures, maybe the first month or so, again talking about reactions from the standpoint of how we can do chemistry on specific functional groups. And what we're going to start with is alcohol. So we'll spend today and tomorrow, isn't that great? 2 days in a row of organic chemistry. Thrilled. Right? Chemistry involving alcohols. Okay? So an alcohol functionality, right, is one in which a carbon of some sort right, is bonded to an OH group, okay? So classic examples, right, if You probably know this, right, from maybe that little time that we spent on IUPAC, right? You're sort of familiar with this terminology. It does differentiate. It's important to recognize that just because something has an OH on it, it doesn't necessarily mean that it's an alcohol. Right, for example, what do I mean by that? As we sort of just showed before, right, carboxylic acids have an OH on it, but we don't generally consider a carboxylic acid an alcohol, although sometimes undergraduates will confuse those a bit. So I'll just make that point to sort of recognize that not all OHs are consistent, and in general, when we're talking about alcohols, we're talking about alcohols generally next to, for the most part, sp3 hybridized carbon atoms, right? And so from a terminology standpoint, if we think about some of the ones that we've seen, right, this would be methanol, right? Methanol is the sort of only one that's sort of bonded to a methyl group, obviously. I'm not going to go through all the subsequent names, but I'll just say that if that carbon something like ethanol, so if that R group was a CH3, that would be ethanol, right? This would be one that we call a primary alcohol. And as will be clear, there's some reactivity differences as we're sort of going through these that makes understanding some of this terminology important, because reactivity of them can change. If it's got two R groups, like isopropanol, for example, that would be a secondary alcohol, right? And then if it's got three alkyl groups to that, right, that's going to be a tertiary alcohol. I guess I'll just draw it over here. So like terbutanol. This would be a tertiary alcohol. Okay? And as we'll see, the chemistry that's involved in these different alcohols reacting can certainly provide different outcomes. We saw last semester, for example, in the case of SN1 versus SN2 chemistry, right, how the ability to form carbocations more easily on tertiary because of stability, we just talked about, makes certain selectivity more difficult on those types of systems where you have tertiary carbon atoms that also could make, so they will go through an alternative mechanistic pathway, right, the SN1 reaction, for example, that will potentially scramble stereochemistry, whereas certain, say, for example, secondary alkyl leaving group type molecules may allow for you to go through SN2 processes, which will have stereochemistry. So again, just sort of reminded of that. Okay, so alcohols are pretty versatile. In part, I just want to sort of start talking about the fact that alcohols, and for the most part, when we talk about chemistry of alcohols, the alcohols themselves are not that reactive, right? When we think about water as the neutral of neutral things, right? Sort of everything is based around water in many cases. That's sort of our sort of almost barometer setting in a way. And so alcohols are very similar, right? The pKa's, the ability to protonate an alcohol, as you might imagine, is very, very similar to deprotonating water. The ability to protonate an alcohol would be very, very similar to protonating water. And so given that, you would likely expect similar pKa's, for example, right? So, and I always like water to start with the pKa, again, because we're familiar with water pKa because of the pH table. And if we're not that comfortable with pKa's, we can think about pH. We all, by this point, know that pH strips we generally think of as like 0 to 14, right? So we kind of know that water's pKa is -1, 0 on the one hand, 14, 15, right, on the other hand. And that should make sense if you understand pH strips, right? Okay, so with that being said, right, you can imagine that with a strong enough base, right, you can take alcohols and you can convert them into anions. Let me just get rid of that because that's going to be dependent upon what you have there. And so with a strong enough base, right, you're going to deprotonate an alcohol. So anything that's got a pKa over, say, 16, right, if you have an OH around, there's a good chance that you might extract that proton, right? What is it? Okay, here. All right, but from a classic standpoint, there's a couple ways that you should know in this class that we make alkoxides. I think the book method that they talk about is sodium 0. I generally don't teach sodium 0, but it's a very practical way to do it in large part because I try to avoid single mechanisms that are sort of radical based as much as I can. I like to try to stick with heterolytic bond formation. But sodium is cheap. It's particularly valuable, say for example, if you want to make a solution of sodium methoxide and methanol. It's very easy to do. You basically just take methanol, you throw a little bit of sodium in there, the sodium reacts, you generate sodium methoxide and methanol. The challenge with sodium in more practical synthesis, so it's really good on scalable like that, like making a sodium methoxide methanol solution. That's where sodium metal would be really valuable. So certainly that comes up a lot in industry and industrial practices where they're trying to make tons of this material. When we're talking about small organic syntheses, more complex synthesis, right? The other challenge with sodium is that because it's a single electron process, sodium can do a lot of other things as well. And so I usually like to just stick with the sort of more classic small molecule, complex molecule chemistry that I'm usually used to working with. And sometimes the book will discuss it, sometimes it won't, but sodium hydride. Okay? Now sodium hydride, I think I've heard the pKa at some point. I don't know exactly what it is, but it's irrelevant, right? It's very difficult to measure the pK of sodium hydride in large part because when the hydride, what's that?
35.
I heard 40.
These all sound maybe reasonable, like maybe lower, I'm not sure. It's irrelevant, right? Why is it irrelevant? It's irrelevant because
We're not going to use
it's reversible. It's irreversible, right? So pKa is based upon thermodynamics, equilibrium, right? One of the ways to perturb that and drive a reaction is Le Chatelier's principle, drive something out of solution. So when sodium hydride reacts, you generate hydrogen gas. And there's very few things that have, lower boiling points than hydrogen gas, right? So hydrogen will escape the atmosphere and effectively drive that reaction to take place. And so sodium hydride is the classic reagent, and it's usually, if I'm going to make a sodium alkoxide upstairs in my lab, that's going to be my go-to reagent. Okay? By the same token, we can also protonate. Right, and so the alkoxide, we've seen alkoxides, for example, behave as bases for elimination chemistry already. We've seen alkoxides potentially behave as nucleophiles for substitution chemistry. So we've already seen methods in which case these alkoxides can be used as reactive intermediates, right? By the same token, if you treat that alcohol with some type of an acid, right, we can now protonate it, right? And again, you would perhaps know at this point that anything that we might imagine could protonate water. So things that are acidic, we've seen a lot of things that are pretty acidic, right? Things like sulfuric acid, things like HBr, HCl, right? These acids, which have pKa's that are oftentimes much lower, they're going to be capable of protonating water. In fact, we saw, I think last semester, those of you that took my class, we discuss sort of elimination chemistry of alcohols within the elimination chapter often. It's a classic example of an E1 elimination process, right? Where we protonate that. We have water be the leaving group, leaving behind a carbocation, which then can eliminate, right? So we've seen examples already, right, where alcohol, by converting it into a more reactive species, can do additional chemistry. And so much of what we learn about reactions of alcohols throughout today and tomorrow is going to follow this same trend. It's going to follow some type of activation, right, followed by additional transformations that would ultimately result. Okay? Okay. All right, so let's start with one that we've probably kind of already seen, but maybe start talking about it in a little bit more depth. Okay. If you let's start with this. So let's talk about synthesis of ethers. I'm going to show a couple different ways that we can do this, and we'll talk about the advantages and disadvantages of each. Okay, so an ether, right? An ether is a molecule, we'll just say R1, R2, right? Where we've effectively replaced one of the bonds of the oxygen, the one that's to the hydrogen, is now going to be replaced by another carbon, right? And so there's different ways in which we can do this, but perhaps the easiest way to do this is under, yeah, Rachel. Well, so hold on. So one of the easiest ways that we can do this, right, is by taking alcohol and treating it with a really strong acid like sulfuric acid. Okay? This is a classic example of a dehydration reaction, right? In part because if we follow through this reaction, what we'll see is that the byproduct of this reaction is water. Okay, so let's go through the mechanism of this process and try to imagine how this might happen. Lucy, please. Okay, so what's going to be the first step of this reaction?
Yeah.
Yeah, well, we just...
You're saying H sulfuric acid, or can I say H3O, or can I just say sulfuric acid?
I would. You should know the structures of everything that
No,
you're
I do know it, but what I mean is, you're saying it's diluted in water, or can I just say H? The H from the closer is the ROH from the sulfuric acid.
Yeah, so right, so HOSO3H, right? So that's the first step. It's protonation, right? That's going to generate water, right? Depending upon the nature of what the R group is, right? We can potentially invoke SN1 type mechanism or SN2 like mechanism. To keep it a little bit simpler, we'll stick with the SN1 mechanism just because we'll break it down. But this is where we lose, right, our water. Right? And through that process, now we generate our electrophilic source, right, of carbon. At this point, another equivalent will come in. Right? It will attack. Right? We'll make this new bond. Right? And then a little bit of liberty here to what you can do, but you have to deprotonate that hydrogen here. Right? Now there's a couple different ways in which we can imagine doing this. We can imagine what's really happening. We can imagine the bookkeeping method. Oftentimes I like to do the bookkeeping method, right? Which basically means somewhere along the line I've lost a proton, let me put it back on that, right? So it's just sort of bookkeeping, right? And so the bookkeeping method would be that we take the sulfonate, right? Because we generated sulfonate when we deprotonated this, right? And so the bookkeeping method would basically just say, and I don't really care which one you use, as long as it's complete, you can take the sulfonate and regenerate sulfuric acid. And that's usually what I'll do just to sort of keep everything together. In reality, the sulfuric acid's probably not what's going to be doing the deprotonation, right? What do you think's probably doing the deprotonation? Yeah. It could be the water, which we'll discuss in a minute. But you're generating the water. Meanwhile, you might have a whole bunch of the alcohol still around as well. So it could be the water. It could be the alcohol, right? Those two, because there's probably so much more of them, right? That's maybe probably what's going to be doing the deprotonation. Okay. Now another point that I want to bring up here, okay, is something. Yeah. You know, another important point that's worth bringing up now. I don't want to overcomplicate this, but I think it's just worth taking a look at really quickly, right? Is that this is a classic example of a dehydration reaction, right? If you look at all the steps throughout this mechanism that I've done, we've generated water, and as we sort of said earlier, water is in many ways, the reactivity of water is analogous. Many of the things that water can do, alcohols can often do, right? And so when we're sort of looking at this mechanism, right, I sort of showed you here, right, that we regenerated sulfuric acid, for example, right? Sorry, lots of arrows going lots of good places. But we regenerated that sulfuric acid. What's to stop that ether, right, from getting protonated by the sulfuric acid? Right, that's an oxygen. It's got lone pairs. You'd be generating an oxyanion. Yeah.
Maybe it does.
Maybe it doesn't. Wait, say it again? Is that what you said?
It does, and then you'll get two products.
No, yeah, well, this is my... right, so certainly taking things and treating it with acid is just bound to lead to lots of products, so yes. But it does. There's nothing that would stop it, is the point, right? Every single step in this entire process that I drew is reversible, right? I can protonate that alcohol. I can deprotonate that alcohol. I can lose the water, right? And then I had the alcohol attack, but that water could also just add right back in. Right? Make sense? Right? I had the alcohol attack here to generate that molecule. Well, the alcohol could just fall off as a leaving group as well. So every single step in this reaction, right, is reversible. So then why does it work? Yeah.
Every product is a more stable product.
No, it's not a thermodynamic argument. It's quite the contrary. In fact, you could run the reaction if you took diethyl ether, for example, and treated it under certain conditions, acidic conditions, you could get it to go into reverse. Yeah.
Because of entropy reasons, you're going from one molecule to two.
Well, no, you're not, because it's really, at the end of the day, it's not entropic, because really it's two equivalents
Right.
of alcohol becoming an equivalent of water and an equivalent of alcohol. So it's not entropically driven. That's sometimes an argument that's made. It's not entropic, it's not enthalpic. Yeah.
Does that have to do with equilibrium?
It has everything to do with equilibrium. But what?
It's stable as it is, so it wouldn't want to go through.
So I said something at the beginning of this. This is a reaction that's going to come up. Yeah. So, yes, well, okay, so I'm asking you guys to read my mind. But this will come up time and time again, so it's a concept that's worth sort of realizing here. Everything is reversible. You can take this reaction and drive it in one direction. You can take the reaction and drive it in the other direction. The difference is water, okay? Water is generated in this reaction. I mentioned earlier about how the pK of sodium hydride was irrelevant, right? Because you generate hydrogen gas, and hydrogen gas leaves the atmosphere, right? Le Chatelier's principle is something that's going to come up quite a bit. You know, you put pressure on one side of the equation, push it the other direction, right? You move something away from one side of the equation, right? Things are going to keep going in that direction, right? You're sort of not allowing it to go in the reverse. Subsequently, if you add an excess of a reagent on one side of the equation, it can push it to the other side of the equation, right? So Le Chatelier's principle is something that is very well often taken advantage of in synthetic organic chemistry to try to get versatility. In the case of water, right, there's a lot of ways in which we can handle the loss of water. People have developed things, for example, called molecular sieves, which will actually, when the water is generated, the water will oftentimes somewhat selectively go into those sieves and drive it out of the reaction. Water is also very unique, right, in terms of its solubility profiles, right? Every time that we talk about solubility, it's oftentimes something else against water, right? So lots of different solvents, right, won't be miscible with water. And so you can oftentimes there's a thing called a Dean-Stark apparatus, which you can go ahead and look up. I'm not going to spend time talking about it. But basically, it's a clever little trick in engineering that basically where you evaporate the water and the solvent, but based upon the way that it's rigged up, only the solvent will return and the water will stay out of the reaction. So chemists have gotten pretty clever at coming up with ways to actually get water out of the reaction and drive a dehydration reaction. So we're going to see quite a few of these dehydration reactions, and they're often driven by trying to remove water from the system. Does that make sense? Okay. Conversely, if you want to go into the reverse direction, that's easy. Right? You just add water. Right? You just add the water, push it, right, and get it to go in the reverse direction. Does that make sense? Okay, so I just wanted to make that clear because considering the reversibility of mechanisms and reactions is really important to something to wrap your guys' head around. Yeah.
Why would you use that instead of something like lineage?
Say that again?
Why would you use that instead of something like sodium hydride?
Oh, okay, so we haven't gotten to Williams and ether synthesis yet. You're asking a question that...
Oh, I mean, because they both make alkoxide. Or they both...
we're going to talk about Williams and ether synthesis next.
So you can blow
Right.
up.
Yes, 1 and then 2, and then we're going to move on.
So in writing the mechanism for this reaction, would you do double-headed error?
No, you don't have to. No, you don't have to. I'm more trying to sort of get you guys to recognize that every single reaction is reversible. And a mechanism, there's going to be some complex mechanisms. I want you guys figuring out how to get from point A to point
So it
E.
doesn't matter for us to do one or reverse it. We'll not get points off of it.
No, but you should keep it in your head. Yeah, Rashida. Yeah, there'll be specific reactions that'll come up later on. A classic example, Rashida, we've seen this last semester, right, is an alkene, right? We can add water across an alkene, right? We add water under acidic conditions. We can also do an elimination of water, right? That phosphoric acid, boiling it off, right? Maybe the molecule that you're making has a lower boiling point than water, so that's another trick that you could do is maybe just boil the water off, right? So we've seen instances in the past, right? Alcohol dehydration, alkene hydration, that's another example of how, we can basically do the same reaction, right, and go in multiple ways. And so every time that something like that comes up, I'll try to make a point of addressing that reversibility. Because every reaction is at its core reversible in theory, right? Every time we draw an arrow in one direction, in theory, we could draw the arrows in the reverse direction. Whether that reversibility has any bearance on actual reversibility and whether or not it's relevant to the chemistry that we're going to talk about, that's a little bit less likely. Or it does happen. It will happen actually quite frequently, but it won't be all the time. But this is a classic example, right? This is clearly an example where you're generating water. I just told you guys when we started off that waters are reactivity-wise similar in many ways to alcohols. So it should make sense that this could also go in reverse. No, we're under acidic conditions here. This is an acid-catalyzed process. We'll get into how to make ethers under base-mediated processes in a second. Go ahead. Okay, look, we'll get to epoxides. Yeah, you're overcomplicating. I'm trying to keep it simple right now. Yeah.
So that you said you use sulfuric acid, but it's a strong acid.
Strong acid.
So it will become a weak acid. I'm sorry, a weak base.
What would? The sulfonate.
The sulfite, yeah.
Well, yeah, I mean the pK of sulfuric acid is I think like what, -2, right? So it's right around the ballpark, I believe, of water, right? So deprotonating this. So this is maybe a slightly weaker base than this. Mm-hmm. Yeah, strong acid, weak bases. It's a relative term, right, based upon what we're specifically talking about. In this case, I'm not sure that that's relevant. Okay, so one of the issues with this is, as we brought up, is oftentimes taking something and treating it with a harsh acid can be problematic. The other issue with a reaction like this, where we have acid-mediated esterification, is that the reaction is going to be difficult to get selectivity. For example, if you want to take one equivalent of alcohol and have it do the same thing with the other equivalent of alcohol, let's say, for example, that we wanted to take, ethyl alcohol and propyl alcohol, and we wanted to make the non-symmetric, right, ether, that's going to be very difficult to do here, right? We could drive it by using a large excess of one, right, and having the other as a limiting reagent. But you can imagine it's going to complicate things because, you can get a lot of, instead of those sort of heterodimers the heteroethers that I'm describing, where you have one on one side, one on the others, you'll get a lot of sort of the more homo ethers where you have the same on both sides. Make sense? Okay, so, and this was brought up by somebody, right, that the way that we can sort of overcome that is effectively by choosing one alcohol to serve as our nucleophile and choosing the other alcohol, I guess, or surrogate, the other carbon, to be our electrophile. It's not going to be our alcohol per se, but it will be that. So in general, if we want to avoid right? If we want to avoid that problem, we want to, say, for example, make an ether and get to these non-symmetric ethers, right? What we can do, right, is we can take an alcohol of one, right? Make the alkoxide, right? And then treat it with the alkyl halide that has the other carbon, right? Does that make sense? Right? And now we're basically doing substitution chemistry. Right, so this is simply right. It's basically SN substitution. It could be SN1, more likely SN2, depending upon the system that we're doing. But this is a reaction called Williamson ether synthesis. And so I would say that at the ground level, this is probably going to be your go-to method for making ethers. In part because there's a control. There's nothing that you could do, nothing that you couldn't make, or there's probably very few things that you couldn't make. Sorry, there's very few things that you could make this way that you couldn't also make using the Williamson ether synthesis, okay? So why do we describe this? It's the same reason why I discussed the sodium versus the sodium hydride. This is a cheaper way. This is a way that's classically used on bulk scales to make certain ethers that are just cheaper to make that way, okay? But there's also some considerations to have. What time are we going with? 10:30, we have 15 minutes. There's also some considerations to have here in terms of choice of what we want to be our alkoxide, right, and what we want to be our halogen. Okay. Because one of the things that we have to sort of keep in mind here is, let's give a classic example, right? Let's say, for example, that we want to make, this is probably the simplest way to explain this, just to start. Oh, I can't drop. So, oh my God. Let's say, let's put an isopropyl group there, right? It doesn't matter, something else at that point. So let's say, for example, that I wanted to make this ether, okay? I have a couple options, right? I have a couple options here. I can either make this from this alkoxide and maybe that bromide, right? Or I can make it from this bromide and this alkoxide. Okay. Now, I want you guys to think for a moment of those two options. Which one do you think would be better? And the hint that I will give you to get you sort of to think about this a little bit more is that one of these has a fairly obvious side reaction. So think about it for a moment, and I'll follow on. Okay. Everybody's had a chance to think. How many people think this is the way to go about it? How many people think this is the way to go about it? So about half the class thinks this way. Nobody said this way, which was unfortunate because I was hoping somebody would say this one and I would call on that person. Oh, you did?
Yeah.
Good. Well, why that one?
Well, what I don't understand, you made that one. Did you already? That one was already isopropyl.
I'm just saying, assume that you could have this and this. Assume that you could have this and this. I want to react these two together. I want to react those two together. Of the two options, you have two choices. Which one would you favor? The bulk of the class said this.
Well, that one requires an extra step. One on
It's the
right.
same step. It's the same step. Same amount of steps. Just substitution. It's both the same reaction, just different nucleophiles. You want to take your answer back? Yeah, I mean there is a potential argument that one might make here, but it's you know it's not at the end of the day, because the major problem, Danny, thank you. I've got to remember some of these names. Danny.
So it's better to have the positive charge on a secondary carbon.
So that could be rationalized. It could be that maybe this is a better electronically. That's sort of more invoking more of an SN1 type argument, though. I mean, I guess you're saying the buildup of positive charge, but it's not this one. And the problem is that this one, yeah.
Just want to ask, isn't it easier to attack primary carbon instead of secondary?
But this is about, and this is what's important about Williamson ether synthesis. You can make the argument either way, right? If you ignore this one-side reaction. Once you bring in this one-side reaction, then it becomes a little bit more obvious. When you're talking about sterics is bad for the electrophile, sterics is bad for the nucleophile, right? The same things that are going to make something bad for, but we're basically doing the same thing. It's symmetric. So, we're just swapping one being sterically challenging for the other. So that you could certainly say a more sterically charged electrophile would be bad, but then you look on the other side, we'll see, well, this one has a more sterically charged nucleophile, right?
Both reactions are possible.
Both reactions can certainly work, but one of them would definitely be the way that you want to go about it. Yeah.
It's not competing. The primary is mostly going to be SN2, but that one's going to compete with elimination.
Yes. Right? The key side reaction that can happen here is elimination. But that elimination can only take place here. Why?
Oh, because it's secondary. Elimination is not going to happen.
Well, what is, for an elimination.
There's no way for an alkene to form.
There's no way for that. Exactly. You don't have that beta hydrogen. You don't even have the extra carbon that can make that double bond, right? It's just a methyl group, right? So the fact of the matter is that you don't have a beta hydrogen here. You cannot have this react with this and do an elimination. Over here, right, you have the possibility for this to serve as a base and eliminate and generate the alkene. And so oftentimes one of the things in Williamson ether synthesis that you want to keep in mind, right, is that if your electrophile that you want to be your, if the group that you have that you want to be your electrophile, if you have the option of not having beta hydrogens, it's probably the one that you should pick. And there'll be discussion in the book that you can read about how sometimes you don't like to have a larger nucleophile and so forth. That starts to get into, I think, some gray area. But the point that I think you should all be able to sort of recognize, right, is now we're learning more reactions. So when we start to see reactions take place, it's worth it to really start to think about some side reactions. And within the Williamson ether synthesis, the recognition, right, is that one of these can do an elimination. One of them cannot, right? Methyl bromide is not the only one that we'll see that can't do an elimination. There'll certainly be others. For example, You know, what if you had one that sometimes comes up as benzyl bromide, right? Benzyl bromide does not have, right? There's no protons there. So you can't do an elimination reaction, right? So that's just another example. So it's not just methyl bromide, but that serves as a good indicator of it. So, okay? Does this make sense? Okay. All right, we've got about 10 minutes left or so. Okay. Okay, so since in Williamson ether synthesis, it requires that we have a halogen, right? Let's now then go ahead and discuss. We didn't have that halogen, we had to make it, right? We know how to take an alcohol and turn it into the alkoxide. If we had an alcohol, how might we make a halogen? They're obviously versatile. How do we do that? And the easiest way to do it, at least mechanistically, although it does have problems, is one that I think many of you could perhaps rationalize based upon what we know. And that is that if you were to simply take an alcohol and to treat it with HBr, right, depending upon the system, right, this is another dehydration reaction, by the way, right? So you can actually drive this reaction in reverse. The loss of water is oftentimes something that you deal with here to potentially do it, but there's other byproducts. So much like esterification, we'll see that there's a better probably go-to way to do this. But at least from a foundational mechanistic standpoint, this is a reaction that's perhaps going to have a lot of parallels to HBr with an alkene, right? So if we think about when HBr react with an alkene, right, we protonated the alkene, left behind a carbocation, right, and then the bromide counterion went in and attacked the cation. Yeah,
Can this create an ether in the same way that
it sure could.
ether, so
It sure
so
could.
it has been byproduct?
Sure could. Thinking how I want you thinking. So absolutely, you can imagine once you protonate that, you have the competition between a Br minus, right? So again, this is where chalkboard chemistry, paper chemistry doesn't necessarily work out. You have to get in there, right? Keep the concentration of the alcohol low, right? Keep the concentration of the bromide Br high, right? Maybe add slow addition of the alcohol. So there's ways around these problems, but this is what synthetic organic chemists will do all the time. It's very rare that an organic chemist runs a reaction and it's 100% yield with no byproducts. It's very oftentimes side reactions, and so it's worthwhile that we consider these. But at least in principle, we could imagine this is a reaction that should be doable. And how would this work? Yeah, it's an acid-base reaction to start. Should be very straightforward. As we'll see, there's other, a little bit more mechanistic, complicated ways to do it. But this is fairly straightforward mechanism that's consistent with what we've seen in the past. We've generated water, or an H2O plus leaving group. Right, this can leave. We leave behind our cation. Bromide then attacks. Right? And that's gonna react. Now, this is, again, much like we were talking about with the ether synthesis, this is not necessarily the go-to way that people are generally going to make alkyl halides, but I just wanted to show this fairly quickly. There's a lot of problems that can be associated with this. In addition to problems associated with, potential crossover esterifications, the buildup of carbocations, right? As we saw, for example, with alkene chemistry, rearrangements are often sometimes possible as well. So the alternative reaction that works a little bit better, and it's sort of more prevalent, is to react this with a PBr3 reagent. Okay? Now here's the thing. That PBr is PBr, absolute ribbon, PBr3 is not, it's hot in here. It's maybe exotic. It's not something that you guys have seen before. But at its core, the mechanism that this is going to go through is really not all that different from what we just saw with the acid, right? What do you think the first step is going to be? Yeah.
The oxygen is going to attack the P and kick out PBr.
Yeah, so the oxygen's going to attack, instead of attacking the hydrogen to leave the Br minus, we're now going to attack phosphorus. Right? We get to the intermediate that I'm showing you there, right? And there's a few different things that we can do here, but the most direct way would be what? Got our bromide, we've got our group, yeah.
For the bromide to attack the carbon and make the rest of it leave.
Yeah, exactly, and that's all that I have written down in my book. It can be a little bit more complex than this, but I think for the standpoint of rationalizing what's happening here, that's perfectly valid, right? And this sort of more SN2-like reaction obviously is going to depend upon the nature of what the R group is, but usually things like rearrangements aren't as likely to happen with PBr. Okay, so I'm just going to finish off with one additional reaction, and just to say that, because we only have a minute left, but if instead of making a bromide, another common halogen, alcohol to halogen reaction is with thionyl chloride. This is one of these reactions that depending upon what book you read, you might get some mixed information because the conditions that people often use with thionyl chloride can actually dictate things like stereoselectivity of these processes. I'm just going to try to keep it simple. Yeah, real quick.
The proton on the still touch the oxygen, but
Oh.
we used to touch the proton.
Wait, where?
Why would it kick out the down then? Where your hand is? That proton. Why would the oxygen rather release the carbon and not release the proton?
So this is kind of where I was going back to earlier, Rachel. You could imagine invoking alternative mechanisms within this that change the order of deprotonation.
Well, also it's not going to make a proton move on its own. Hydrogen on its own, like a proton on its own is one of the most unstable things.
Sure. Here, let me just, because we only got like a minute left, guys. Let me just I just want to get through this one more halogenation reaction, then you guys can ask questions afterwards. So this one I'm just going to, again, try to keep as simple as possible. Chlorination chemistry is similarly, it's similarly going to effectively take, instead of PBr3, you're going to take thionyl chloride. Again, you can invoke almost the identical mechanism that we just showed, right? And again, depending upon what book you get this from, this is one of these reactions that is, how do I put it? It's in, some people try to act, it's a lot more complicated, let's just say. And so some people try to embrace that complicated nature. We've got a lot of reactions to go through. I'm just going to try to keep it simple. And just try to make it analogous to what we saw in the past. Oftentimes this is run with a base. Choice of base can have a dramatic influence on what happens here. I'm just going to show it without the base because that also works. And just to keep it analogous to PBr3, we're going to get our alkyl chloride. One of the things about thionyl chloride is the byproduct of this reaction that I've shown you there. Again, the sequence, and depending upon whether you use base or not, you might not necessarily generate this intermediate, but you can probably tell, for example, that if you did have a little bit of base, a weak base perhaps, but you could perhaps see that the equilibrium here could actually favor HCl and SO2 gas, right? So SO2 would be a gas. And so oftentimes when a base is used in this, it'll be maybe sodium chloride and SO2 gas. But you liberate SO2, and this is another thing that drives this reaction. So, okay, so we're out of time. Tomorrow we're going to continue talking about additional alcohol reactions. We're going to learn a lot next class. These are some of the more simpler mechanistic ones. We may get into a little bit more complicated ones, but all right, I'll see you guys tomorrow.